So this chapter is all about alkenes and mostly about elimination reactions, and the connection between them is that elimination reactions we're going to study form alkenes as products. So we've got to talk about alkenes a little bit first, and a compound is simply an alkene if it has a carbon-carbon double bond, and we're going to name them first. And the first rule is you want to find the longest continuous carbon chain that includes the carbon-carbon double bond, that includes the alkene. This is different from what we saw with alkanes. With alkanes, we wanted the overall longest continuous carbon chain. So here it's the overall longest continuous carbon chain that contains the alkene. In some cases, that might not be the overall longest carbon chain. So just an FYI. You're going to number the chain, so get that alkene the lowest possible number. So in this case, we'd number this one left to right. 1, 2, 3, 4, 5, 6, and 7. So if you notice the alkene here is between carbons 1 and 2, you always give it the lower of those two numbers. So in this case, carbon 1. We're going to name the alkene with an ene suffix. So 7-carbon alkane will be heptane. A 7-carbon alkene is going to be called heptene instead. And then finally, the alkene's chain locator, in this case, again, we're saying it's located at position 1, comes in one of two places, either before the parent chain or right before you say "ene." We actually stick it in the middle of a word, and we'll find out in some cases in the future when we got multiple functional groups named in the parent chain, you've got no choice but to put numbers in the middle of the parent chain name. But in this case, either way, both are going to be acceptable here where we've got just the one functional group. And so in this case, we could call this 1 heptene, or we could put, again, the chain locator in the middle of the word, so hept-1-ene. Both are acceptable. If we take a look at the next example here, so the longest continuous chain containing the alkene is 1, 2, 3, 4, 5, 6, 7 carbons. This is going to be some form of heptene again. If we number it left to right, the alkene would be between 3 and 4. If we go right to left, it would be between 4 and 5. So we definitely want to go left to right, so 1, 2, 3, 4, 5, 6, and again, doesn't really matter which one of these is number 7. In this case, I've got a methyl group at 6, and I've got an ethyl group attached at carbon 3. So we're going to name the substituents first, just like we did with alkanes, and name them in alphabetical order. So we'll start with the ethyl. So this will be 3 ethyl, 6 methyl, and then we got two options again. We can say either 3-heptene or hept3-ene, so I'll do it both. So in this case, 3-heptene. I just like the sound of that better, but again, we could also everything up till methyl here and just do hept-3-ene. So 3-ethyl-6-methyl hept3-ene would also be acceptable and in often cases preferred. If your professor has got a preference for one or the other, obviously run with it, but both are acceptable by IUPAC. So here I want to show you an example of what to do when an alkene is part of a cyclic structure, a ring in this case. Your ring that contains the alkene will be your longest chain, and you'll have to number it one of two ways. Your alkene will be either 1 and 2, or 1 and 2. So you've got to number through the alkene as carbons 1 and 2. And in this case, from there on out, then at that point, it's all about the substituents. So if I number through as I'm doing in blue around clockwise, my substituents, my methyl groups would both be at carbon 3. Had I numbered it around in red, 1, 2, 3, 4, 5, they wouldn't have been till 6. So the blue way is superior here. And so in this case, we'll name our substituents 3, 3 dimethyl. So, and then we'll say cyclohexene. And in this case, we don't have to give the location. If we're naming it as cyclohexene, it's implied that the alkene is between carbons 1 and 2 and has the designation 1 in this case. So you wouldn't say 3,3-dimethyl 1-cyclohexene or cyclohex-1-ene. You actually leave the 1 out specifically in this case. As we saw in the chapter on stereoisomers, a carbon-carbon double bond is not free to rotate. The sideways overlap of the p orbitals would be broken if you tried to rotate that bond. And as a result, a couple of different stereoisomers are possible that we often refer to as cis and trans. And if we take a look at this, if each side of the alkene, each of the sp2 carbons, so this sp2 carbon, say, and this sp2 carbon, if they're both bonded to the same two groups, it's appropriate to use the terminology cis and trans. So in this case, the two like groups, if they're 60 degrees apart, as they are in this case, we refer to that as cis. And if they're 180 degrees apart, so notice the two methyls point opposite each other, and the two hydrogens point in opposite directions. So when that's the case, we refer to it as being trans instead. And so just referring to this compound as 2-butene or but2ene would not be sufficient. We've got to add that cis label on the front. So in this case, this could be cis-2-butene or cis-but2ene, same diff. So, and the one below here would be trans-2-butene. butene. So saying just plain old 2-butene is not specific enough because there's two compounds that could potentially go by that name. We've got to imply stereochemistry here with the cis and trans designation. We'll see with some more complicated ones, cis and trans may not be appropriate. So here we've got another example, and in this case we can still use cis and trans, it turns out, even though the two sp2 carbons don't necessarily have the same two identical groups. So in this case, the sp2 carbon on the left's got a methyl group here and a hydrogen, and the sp2 carbon on the right's got a hydrogen and an ethyl group. But the key is, as long as both of the sp2 carbons have exactly one hydrogen, we can still define it as cis and trans based on how those hydrogens are related. So in this case, the two hydrogens are 60 degrees apart, so we'd refer to this as cis. So, and the one down below, those two hydrogens are 180 degrees apart, so this would be the trans isomer. So in this case, we'd number it left to right, 1, 2, 3, 4, 5, and so this is 2-pentene or pent-2-ene. I'll use the latter in this case. So pent-2-ene or trans pent-2-ene. So even if both sides, again, don't have the same two groups, but as long as each side have exactly one hydrogen, we can use the relationship of those hydrogens to designate the two compounds as cis or trans. With the last two stereoisomers there for cis-2-pentene and trans-2-pentene, or cis-pent-2-ene and trans-pent-2-ene, it turns out we could use another designation as well, and it turns out you can always use this other designation, and it refers to E and Z. Now, E and Z are German words, entgegen and zusammen, and they mean on opposite sides and same sides and stuff like that. The German words are not important, but being able to assign E and Z is what is important. So the way it works, you're going to use those same Kahn-Ingold Prelog rules we use to assign R and S, and what you're going to do is you're going to assign one of the two groups attached to each of the sp2 carbons as a higher priority. So in this case, for the sp2 carbon on the left, it's bonded to the carbon of a methyl group and a hydrogen, and carbon's got a higher atomic number, so I'm going to circle that as the higher priority group. So, and then the sp2 carbon on the right here is also bonded to two groups, a hydrogen and the carbon of an ethyl group. So that carbon of the ethyl group is going to get the higher priority. And in this case, those two higher priority groups are cis to each other. So, and when the two higher priority groups are cis to each other, we refer to it as the Z isomer. And we often say they're on the same side as a way of remembering that. So in this case, instead of calling this cis-2-pentene, we could call it Z, and you put the Z in parentheses, and then 2-pentene, or again, pent-2-ene, same diff. So if you did the same thing on the molecule over here, for the sp2 carbon on the left, he's bonded to a hydrogen and a carbon, and again, the higher carbon gets the higher priority, and a hydrogen and a carbon for the one on the right, and again, the carbon gets the higher priority, and now they're trans to each other. When the two higher priority groups are trans to each other, we refer to it as the E isomer, and so this would be E2-pentene, or again, E-pent-2-ene, same diff. So this is the EZ system, and we'll find out again, in the cases we've been looking at here, whether we use E and Z or cis and trans, you could go with either way. But with some more complicated examples here, we're stuck using only the E and Z system. The cis and trans system would be a little bit ambiguous, as we'll see on the next slide. All right, in this next example here, if we use the terms cis and those designations, we'd have a little bit of a problem, because what exactly are we saying is cis and trans to each other? Both sides do not have the same two groups. Neither side has a hydrogen, so it gets a little bit ambiguous, and this is where you have to use the E and Z system. So for the sp2 carbon on the left, he's bonded to a bromine and a hydrogen. The bromine's got the higher atomic number. So, and for the sp2 hybridized carbon on the right, it's bonded to a carbon and a chlorine, and chlorine's got the higher atomic number. And so in this case, those two groups are on the same side, if you will, or in this case, they're cis to each other. Sometimes people say, draw a line after your designations through the double bond, and if the two groups end up on the same side, that's the Z isomer. So this is the Z isomer. I'm not going to name the whole thing. I just want to designate it as E or Z on this slide. So if we go down to the one right below it, so on this sp2 carbon, the bromine's got the higher priority, and on the sp2 carbon on the right, the chlorine's got the higher priority, and so now the two higher priority groups are trans to each other, or again, if you drew that line right through the double bond, they'd be on opposite sides, and that is the E isomer. And also do the same thing down on the bottom one here. So, and this one's going to be a little bit more complicated here. I'm going to start with the carbon on the left. So in that carbon on the left, it's bonded to a carbon, and it's a tie. And just like we did with assigning R and S, we'll use those Kahn-Ingold Prelog rules for breaking the tie here. So in the carbon up top here, it's got 3 additional bonds. There's 2 hydrogens not drawn in and a fluorine, and we'd rank those in descending order of fluorine, hydrogen, hydrogen. So, and then this carbon down below is bonded to a carbon and 2 hydrogens, so carbon, hydrogen, hydrogen, and we see that the first point of difference is fluorine's going to beat hydrogen, so there's our higher priority group. So a little bit complicated here when there's a tie. Same thing here for the sp2 carbon on the right. It's bonded to a carbon down below a methyl and the carbon of an isopropyl, and we see that the carbon of the methyl, its 3 additional bonds are to all hydrogens, and the carbon of the isopropyl is bonded to 2 carbons and 1 hydrogen, and the first place of difference, carbon beats hydrogen, so this is the higher priority group, and we see that the 2 higher priority groups we've now circled are on the same side or cis to each other, and so this is the Z isomer. So this is how we go about designating E and Z, so very similar to what we did with R and S. So now we want to take a look at how you name a polyalkene when you've got multiple alkenes in the same molecule here. And it turns out in the parent name, instead of just saying ene, you're either going to say diene, triene, tetraene, so on and so forth, describing the exact number of alkenes you have in your molecule. You still want to find the longest continuous carbon chain that contains all the alkenes if possible, and you want to number it in such a way to get the first alkene you encounter the lowest possible number. So in this case, we can see that our longest chain here would be 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that contains all the alkenes, and I numbered it right to left here. That way the first alkene I encounter would be at position 1. Had we gone the other way, the first alkene we encountered wouldn't have been till position 2. In this case, we've got a methyl group on carbon 3, an ethyl group at carbon 4, and another methyl group at carbon 7 there. We'll name all the substituents first here, so I want to leave myself some room because we'll have to worry about some E and Z considerations in a little bit. But in this case, ethyl comes before methyl, so we'll say that first. So it's 4 ethyl, and then we've got methyls at 3 and 7, so 3, 7 dimethyl. So now the real fun here. So 9 carbons is non for the prefix. So, and in this case, if it were just one alkene, we'd say something like non-ene and figure out where to put the chain locator. But with 3 alkenes, we're going to say non-triene. So in this case, I'm going to put the designators right in the middle of the word. So but right before I say triene, I'm going to give those 3 locations. So one is at position 1. One of the alkenes is located at position 4, and one of them is located at position 7. So we'd say nana 1, 4, 7 dash triene. So this is 4-ethyl 3,7 dimethyl nana 1,4,7 triene. And again, we could have put those chain locators right before the parent chain and said 4-ethyl 3,7 dimethyl 1,4,7 nana triene as well. We're not done though, so whenever you've got an alkene, you want to take a look and see, is it possible to have stereoisomers, both E and Z, and then if so, which one do you have? So we look at the first alkene here, so on position 1, I'm going to draw in the fact that this sp2 carbon is bonded to 2 identical hydrogens. And if it's bonded to 2 identical hydrogens, I can't give either one a higher priority. And so it turns out if either side of an alkene, either of the sp2 carbons, is bonded to 2 identical groups, there's no such thing as E and Z. It's not possible for it to have multiple stereoisomers. It just exists the way it does, the only way that's possible. So there's no E and Z designation here for that alkene. If we go to the alkene between 4 and 5 here, we've got the sp2 carbon at 4 and the sp2 carbon at 5. The sp2 carbon at 4 is bonded to the carbon of an ethyl and the carbon of this group right here. The carbon of the ethyl is bonded to a carbon and 2 hydrogens. This carbon, carbon number 3 specifically here, is bonded to 2 carbons and a hydrogen. In the first place we see the difference, and carbon 3 is going to win the higher priority. Now if we go to the other side here, carbon 5, that sp2 carbon is bonded to this carbon right here and then not drawn in as a hydrogen, and the carbon's going to win the priority. And we see that our 2 high priority groups, especially if we draw that line again through the double bond, are on opposite sides. They're trans to each other, so that is an E designation. So, and then if we take a look at the other carbon-carbon bond over here, so between 7 and 8, so sp2 carbon at 7, sp2 carbon at 8. So the sp2 carbon at 7 is bonded to a carbon, as well as another carbon of a methyl. The carbon of the methyls got 3 hydrogens. The carbon, it's carbon number 6 here, is bonded to 1 other carbon and 2 hydrogens. And the first point that's different, we'll see that he's going to win the higher priority. And then carbon number 8 is bonded to carbon number 9 as well as a hydrogen, and carbon beats hydrogen atomic number. And in this case, we also see that our 2 higher priority groups are on opposite sides again if you drew that line, or they're trans to each other, and that's also an E designation. Now, if you've only got one alkene that is, going to be assigned E or Z, you just put E or Z in parentheses at the beginning of the name. But if you've got more than one, as we do here, you not only only have to say E and Z, but you have to give the chain locator number where the alkene's located as well. So we'll put these in parentheses. Instead of saying just EE, we've got to specifically say 4E, comma 7E in this case. To identify it. So again, with only one alkene, you just say E or Z. You don't give the chain locator. But when you've got more than one alkene that's going to be designated as E or Z, you've got to give the chain locators as well.